Welcome. We spoke at the beginning about the fact that leptonic mixing means that each neutrino of definite flavor is a superposition of the mass eigenstates. Now, of course, one can invert that relation to express each mass eigenstate as a superposition of the flavors. And as you see, the flavor alpha fraction of mass eigenstate nu I is just the square of u alpha I. What that means is that when nu I interacts and produces a charged lepton, the probability that that produced charged lepton is in particular of the flavor alpha is just u alpha I squared. So I showed you before the mass squared spectrum in either its normal or its inverted form. Here it is again, but this time showing by color coding the flavor content of the various mass eigenstates to the degree that we know it experimentally. The nu E fraction, that is to say u E I squared of a mass eigenstate in green, the nu mu fraction in red, the nu tau fraction in blue. And once again, what these fractions mean is if this mass eigenstate interacts and makes a charged lepton, the probability that that charged lepton is in particular an electron is the green fraction of this neutrino. The fractions being normalized to 1. Okay. Now you see that these colors are widely distributed. One thing we actually don't know is how big the nu E fraction of the isolated neutrino is, regardless of whether it's at the top or the bottom. We know only that at 2 sigma, this fraction, which is parameterized in terms of a mixing angle called theta 1,3, is no bigger than about 3% of that neutrino. Now, these fractions tell you the sizes of the various elements of the mixing matrix. But if you want to talk about the signs or the phases of those elements, we have to go to the matrix itself. Assuming that it's 3 by 3 and unitary, the mixing matrix can be written as a product of 4 factors like this. One of them involves nothing but phases which are called Majorana CP violating phases. They do not affect oscillation. The rest is just like the way you write a rotation in terms of a product of 3 Euler rotations, each of which depends on 1 Euler angle. And you can do the same thing here. The first factor depends on the cosine and the sine of a mixing angle theta 2,3, which dominates the behavior of atmospheric neutrinos. So it is measured in the atmospheric oscillation experiments. And the best fit is actually maximal mixing, which means cosine theta equals sine theta, or in other words, theta equals 45 degrees. But at 90%, there's still a considerable uncertainty. One factor involves a mixing angle theta 1,2, which dominates what the solar neutrinos do, and that's also very large. It's not 45 degrees, but it's 34 plus or minus something like 1.5 degrees. Finally, there is this cross-mixing 1,3 mixing factor in the middle. It involves this mixing angle I called theta 1,3, about which we know only that that number is less than 0.03, or correspondingly, theta 1,3 is less than something like 11 degrees. This final factor can also involve a CP violating phase delta, and if it does, that will produce a CP violating difference between the probabilities for corresponding neutrino and antineutrino oscillation. These factors do not affect oscillation, but that one would cause a CP violation. Notice, however, that delta enters into the mixing matrix and hence enters into physics only in combination with the sign of theta 1,3. Consequently, the size of any such CP violation is going to depend, among other things, on the sign of theta 1,3. So that number is very important. there have been some hints from existing experiments that theta 1,3 is not 0, but these hints are not very strong yet, so I decided not to mention them. Now, if you look at this, you may be wondering about the following question. What is so special about theta 1,3? Why is it that the CP violating phase occurs next to theta 1,3? Why doesn't it occur next to theta 1,2 or theta 2,3 or all of them? That's a good question. I'm glad you asked it. There is actually nothing special about theta 1,3. If you multiply out all of these factors and then you plug that matrix into this master formula and you work out, for example, the difference between nu mu to nu e and nu mu bar to nu e bar, this is what you're going to find. Notice that this CP violating difference vanishes if any of the mixing angles is 0. Theta 1,3 or theta 1,2 or theta 2,3. And of course it vanishes if the CP violating phase isn't there. Now, the fact that it depends on all three of these angles should not be a surprise. Kobayashi and Miskawa won a Nobel Prize for showing that the quark mixing matrix could violate CP, but they discovered that it could do that only if there are at least 3 quark families. And they didn't say so explicitly, but obviously those 3 quark families have to all be mixed. Because, for example, if 2 of them mix, but the third doesn't mix with the first 2, then the first 2 don't know that that third family is there. And so there isn't enough physics to violate CP. It's the same thing here. If any one of these mixing angles vanishes, then I can find some basis in which I have 2 interacting states and a third one which is decoupled entirely from the 2 interacting states. And there's not enough physics to violate CP. So all of the angles have to be non-zero. However, this sine 2 theta 1,3 is approximately 1 experimentally. Theta 2,3 is about 45 degrees. This sine 2 theta 1,2 is a big number also. This angle is 34 degrees. The only thing we don't know is sine 2 theta 1,3. So to emphasize that the size of any CP violation is vulnerable to this, the only unknown angle, we have chosen as a choice to put this phase factor next to theta 1,3. We could have put it next to theta 1,2 instead. The physics consequences would have been exactly the same. Now finally, here is the spectrum. I'll take it to be in its normal form just so we can talk about it. And I'll try to summarize for you where the various pieces of this picture of what we know experimentally came from. Let's start at the top left. Reactor experiments have been done, some of them, with a detector about 1 kilometer from the reactor. Now, the energy of neutrinos coming out of a reactor is about 3 MeV. That results in an L over E, which makes the experiment sensitive to this big gap, but insensitive to this little one, so it thinks these 2 neutrinos are 1 neutrino. In an experiment like that, a formula of this form holds, and this effective mixing angle measures the flavor content of the neutrino that's at one end of the delta m squared that the experiment can see. What these experiments looked for is the disappearance of neutrinos coming out of a reactor as they travel a kilometer. Now, those neutrinos are electron neutrinos because reactors involve nuclear reactions which involve electrons or positrons. They happen to be nu-E bars, not nu-E's, but that's irrelevant. They're electron neutrinos. These experiments do not see any disappearance at 1 kilometer, so they put an upper limit on the degree to which this neutrino couples to an electron. The degree to which it couples to an electron is just what we call its nu-E fraction. So that's what gets limited. And it gets limited to about 3%. All right? Now, apart from this possible 3% or less, the rest of the neutrino is nu mu or nu tau. The atmospheric experiments start with muon neutrinos, and they see that they oscillate big time. In fact, the oscillation is as big as it can be. 45-degree oscillation. What that means is that one of these pieces, which is cosine of some angle theta, and the other of these pieces, which is sine of that same angle theta, are equal. So, apart from this 3%, nu 3 is just a 50-50 mixture of nu mu and nu tau. Going downhill, what's observed is that when atmospheric neutrinos travel through the entire diameter of the Earth to a detector, they oscillate. They disappear. Half of them go away. But when neutrinos come down from above the detector, so they're only about 1 kilometer, the thickness of the atmosphere, away, they don't oscillate. Plugging that into this formula bounds this delta m squared from above and from below. And of course, the experiments do much better than that. And that's how this gets the value that it gets, which I quoted before. It's about 2.4 times 10 to the minus 3 electron volts squared. Moving to the closely spaced solar pair, the matter in the sun through which solar neutrinos travel on their way out from the solar core where they are made to the outer edge of the sun influences their flavor change very much. And the flavor change is described by what's called the large mixing angle Mikheyev-Smirnov-Wolfenstein effect. And that has the consequence that what comes out of the sun, once the neutrinos get to the outer edge, 90% of them are this mass eigenstate. Not a nu E, not a nu mu, not a nu tau, nu 2. So the sun is a source of a flux of a mass eigenstate. And of course, a mass eigenstate is an ordinary particle, like a proton. It doesn't oscillate into anything. Mass eigenstates don't oscillate. If they did, that would violate energy conservation. So this nu 2 that comes out of the sun propagates all the way to the Earth. Still is a nu 2, and it gets here. It's a nu. Whereas I don't know which way is west, but the sun is down there somewhere. They're coming right now. Nu 2s upwards from the floor. The probability that this neutrino from the sun is going to make an electron in a detector that's looking for it to do that is just the electron, the nu E fraction of this neutrino, the green fraction. That's measured to be about, the probability of making an electron by a solar neutrino is measured to be about 1/3. Consequently, the nu E fraction of this neutrino has been determined from solar experiments to be 1/3. Now, unitarity of the mixing matrix says that the sum of all the 3 nu E fractions of the 3 neutrinos has to add up to 1 neutrino's worth. This one is small. This one is 1/3 of a neutrino. Therefore, this one has to be 2/3 of a neutrino. The rest of these 2 neutrinos are nu mu and nu tau. For the same reason that this is a 50-50 nu mu nu tau mixture, if that mixing angle is really 45 degrees and not 51 degrees, but it's approximately something like this. For the same reason that it's this way up here, these two neutrinos together must be the orthogonal 50-50 mixture, nu mu minus nu tau over square root of 2. That doesn't tell you that nu mu and nu tau occur in equal proportion in these two neutrinos separately, but that is also true, and it's very easy to show. Finally, the splitting between the two closely spaced neutrinos can be measured by solar and by reactor experiments. This is best measured by a reactor experiment which has its detector not 1 kilometer but 180 kilometers away from a whole bunch of reactors. So it is much bigger L, and hence it is sensitive to much smaller delta M squareds, and it is sensitive to this gap, and has given us a very nice, accurate measurement of that gap. The way they measure it is they're looking for Newey bar disappearance. The distance to the reactors is fixed, but the energy isn't. They're looking at a spectrum of reactor neutrinos, and consequently they can study that spectrum as a function of E, and that's going to determine what this coefficient is. That's how they did it. That's how we learned what we know. Now, what we know has raised some questions. First of all, what is the absolute scale of neutrino mass? How far above zero is the whole pattern? We don't know that yet. Are neutrinos, unlike the quarks and the charged leptons, their own antiparticles? What are the dipole moments of neutrinos? What is this angle theta 1,3 on which CP violation depends? Is that atmospheric mixing angle really 45 degrees? If it is, that's very interesting, because when something like that happens, maximal mixing, there's usually a reason, a symmetry or something. Is the neutrino spectrum quark-like or inverted? Do neutrino interactions violate CP? That is, do antineutrinos and neutrinos behave differently? We said neutrinos are abundant. What can neutrinos in the universe tell us about each other? In particular, is CP violation involving the neutrinos the key to understanding the matter-antimatter asymmetry of the universe? I'm going to skip stuff if I need to in order to be sure to get to this. What physics is behind neutrino mass? And while we have our eyes fixed on these questions, watch out, there may be surprises. Now, what I'd like to do in the rest of the time is talk about just a few of these questions. My God, it's 25 after 9. Just a few. What's the question? Why is it interesting? How can you go about answering it through future experiments? Being a realist, I'm going to skip this one. I'm going to do what I threatened to do. There are certain things I want to be sure we get to. So I'm going to, I don't know how many to skip. Let me take a pot shot. Is the antineutrino the same as the neutrino? First of all, what's the question? What does it mean? The question is, for each mass eigenstate, for each physical neutrino particle, not which a nu E isn't, but for each mass eigenstate, and for given helicity h, is the antineutrino the same as the neutrino, in which case we call the neutrinos Majorana particles, or is the antineutrino different from the neutrino, in which case we call them Dirac particles? An equivalent question is, do neutrinos have Majorana masses? Because if they do, then the mass eigenstates are like this, Majorana particles. So what's a Majorana mass? An example is a mass term like this, which absorbs a right-handed antineutrino and makes a left-handed neutrino. As this illustrates, what any Majorana mass does is to turn an antineutrino into a neutrino or the other way around. So they mix nu and nu bar, and consequently they don't conserve the lepton number L that distinguishes leptons, neutral and charged on the one hand, from antileptons, neutral and charged. This is not lepton flavor. It's leptonness versus antileptonness. It's the leptonic equivalent of the baryon number that distinguishes a neutron from an antineutron. That's what this quantum number is. If there are terms like this which mix nu and nu bar have opposite values of this quantum number, then obviously this quantum number is not conserved. So Majorana mass terms explicitly violate L conservation. Now, why does the presence of a Majorana mass term have the result that neutrinos are their own antiparticles? Rather than going through the mathematics, I'll give you the hand-waving answer. You know about neutral kaons, right? As a result of K0, K0 bar mixing, the neutral K mass eigenstates are not K0 or K0 bar, but rather the states which are called K short and K long. Neglecting CP violation, these are just the sum and the difference of K and K bar. So what you see is that apart from an overall sign which is irrelevant, either of K short or K long goes into itself under particle-antiparticle interchange. So K short and K long are what you might call Majorana bosons. In a similar way, the Majorana mass term induces a nu-nu bar mixing, which is analogous to this K-K bar mixing. And as a result of this nu-nu bar mixing, the neutrino mass eigenstate will not be nu or nu bar. It's going to be their sum. And when I make a nu into a nu bar and a nu bar into a nu, this sum, of course, doesn't change. So the neutrino is its own antiparticle, and that's why Majorana mass terms, which are like this, make nu bar equal nu. Mass term. For any fermion would mix that fermion with either its own antifermion or a closely related antifermion. This mixing, if the fermion is electrically charged, would reverse the sign of the electric charge, turn electron into positron. Well, that would violate electric charge conservation. That's a very big no-no. So an electrically charged particle cannot have a Majorana mass term. But neutrinos are electrically neutral. So they could have Majorana mass terms. And if they do, that's going to make them very different from the quarks and the charged leptons, because a Majorana neutrino mass necessarily has a different origin than the quark and the charged lepton masses. In the standard model, the quark and the charged lepton masses come from a Yukawa coupling of the quarks or of the charged leptons to the Higgs field. A Yukawa coupling of a neutrino to the Higgs field would generate what is called a Dirac neutrino mass term. It's the analog of the quark mass term. It is not a Majorana mass term. It does not mix neutrino and antineutrino. If there are Majorana masses, that makes the neutrinos very different, because the origin of their masses, at least the Majorana piece of it, has an origin that nobody else that we know of, no other particle, shares. Now, I know that Dirac neutrinos, Majorana neutrinos are a little bit unfamiliar, particularly the Majorana neutrinos. So what's a Dirac neutrino and what's a Majorana neutrino in the context of the standard model interactions? First, a Dirac neutrino. A Dirac mass eigenstate plus its antiparticle is a collection of 4 states with a common mass. I'll denote the momentum by the long arrow and the spin by the short one. So we have a left-handedly polarized neutrino, a right-handed antineutrino, a right-handed neutrino, and a left-handed antineutrino. When this left-handed neutrino interacts and makes a charged lepton, that charged lepton will be negative. And when this right-handed antineutrino interacts, what it makes will be positive. In the Dirac picture, we understand that in terms of lepton number conservation. In the Dirac picture, there is a conserved lepton number. That's the difference between nu and nu bar. Nu has L equals plus, nu bar has L equals minus. And L is conserved. And L minus, like an electron, also has L equals plus, and L plus, like a positron, has L equals minus. So that's why this particle makes L minus, and that one L plus. The Standard Model also has the feature that its currents are left-handed. That means that when there is a difference between fermion and antifermion, between neutrino and antineutrino, it's only the left-handed neutrino that interacts, and only the right-handed antineutrino. So the right-handed neutrino and the left-handed antineutrino do not interact. At least they don't in the limit that these particles are highly relativistic, which they always are in the experiments that we do. These states are there, but they don't interact. So you might ask, well, if they don't interact, how do you make them? That's a very good question. I'll leave you to puzzle over it. There will be a quiz. Now, in contrast to that, a Majorana neutrino is just two states of a common mass, a left-handed one and a right-handed one. As before, this left-handed one, when it interacts, makes a negative charged lepton, whereas this right-handed one makes a positive charged lepton. In the Majorana picture, we do not understand that in terms of lepton number conservation. There is no conserved lepton number now. If there were, this particle and that one would be different. But in the Majorana case, they're not. In fact, there is no difference between this particle and that one other than their opposite polarization. So you can just erase that bar. The only difference between these two particles is their handedness, their polarization. But we know that the weak interactions of the Standard Model violate parity. That is to say, they distinguish a left-handed particle from a right-handed particle. That's why there are these L's in here. As a result of that distinction, and you can bear it out by staring carefully at that Lagrangian, an incoming left-handed neutral lepton is going to make an L minus, while an incoming right-handed neutral lepton is going to make an L plus. And that's how these two particles get to make different final states. All they needed to have was different polarizations. They don't need to have a conserved lepton number. Polarization is sufficient because the weak interaction cares about the polarization. Now, of course, a neutrino, Majorana or Dirac, is totally electrically neutral. But you might ask, can it have an electric charge distribution inside, adding up to 0? For instance, could there be a positive core surrounded by an equal and opposite compensating negative shell? Well, this cannot be there if it's a Majorana neutrino, because the antiparticle to this system is obviously, since charges reverse under particle-antiparticle conjugation, a negative core surrounded by a positive shell. Well, this thing is obviously different from that thing, but the antineutrino in the Majorana case is the same as the neutrino. So a Majorana neutrino can't look like that. There is a more mathematical way of proving the same thing, but this is essentially the point. A Majorana neutrino not only is overall electrically neutral, it's very electrically neutral. It hasn't got any charge distribution inside either. Suppose you have no Majorana masses, just a Dirac mass and a corresponding Dirac neutrino, 4 states. And now you turn on a Majorana mass. what it will do is split this Dirac neutrino with 4 states into 2 Majorana neutrinos, each of which has just 2 states, a left-handed one and a right-handed one, and there is no antineutrino distinct from the neutrino. So you can remember this behavior by simply recalling that 2 plus 2 is 4. Now, how can you determine experimentally whether there are Majorana neutrino masses? The promising approach is to look for neutrinoless double beta decay, or zero neutrino beta-beta decay as it's called. That's the process in which one nucleus decays to another by emitting 2 betas and nothing else. If you see this reaction, which has not been confirmed so far, at any non-zero level, you will demonstrate that there is in nature a Majorana neutrino mass term. Because at the quark level, neutrinoless double beta decay is 2 down quarks turning into 2 up quarks and 2 electrons. If you see the reaction, you know that the amplitude for this is non-zero, whatever is in the black box. And you know also that the W boson connects quarks to leptons. So if the amplitude for this is non-zero, so is the amplitude for that. But this process converts a right-handed antineutrino into a left-handed neutrino. That is exactly what the Majorana mass term I gave you as an example does. So if neutrinoless double beta decay is non-zero, nature does contain an amplitude which has the effect of a Majorana mass term. This is higher order. It may be a very tiny Majorana mass term, but it's a Majorana mass term. And because of that K0, K0 bar argument, if there are Majorana masses, then the neutrinos are their own antiparticles. There's a lot of interest in doing this experiment. Various experiments are under development throughout the world. Now, the final question I wanted to get to: do neutrino interactions violate CP? Well, what I hope to convince you is a very closely related question. Are we, you and I, descended from heavy neutrinos? Now, I'm going to say more about this tomorrow morning, but I want to go through it at a sort of a more hand-waving level here. The universe confronts us with a big challenge. A cosmically broken symmetry, because it contains baryons, the nucleons of which we are made, but essentially no antibaryons. The baryon number of the universe defined as the number of baryons minus the number of antibaryons, or what's the same thing, 3 times the number of quarks minus the number of antiquarks, since there are 3 of these per baryon, is observed to be non-zero. Yet, standard cosmology tells us that if this number had been non-zero right at the beginning, at the moment of the Big Bang, any initial non-zero baryon number would have been erased by several different physical processes. So shortly after the Big Bang, B was 0, and yet today it's not. How does 0 turn into not 0? Sakharov taught us long ago that this cannot happen without a violation of CP. That's sort of obvious. CP violation just means that matter and antimatter behave differently. Now, if you start with B equals 0, that means you have equal numbers of baryons and antibaryons. And if the 2 behave the same, then whatever the one does, the other does too. So you're going to continue to have equal numbers of baryons and antibaryons. But that's not what we see today. So CP must be violated. Now, CP is observed to be violated in the quark mixing matrix by a quark analog of that thing I call delta. However, that CP violation is it's not that it's too small, it is of a character that would lead to much too small a baryon number, much smaller than the baryon number that we see. Well, if the quarks can't do it, an obvious question is, can the leptons do it? even though it's a baryon number we're trying to explain. And let me parenthetically explain to you why it's a baryon number we're trying to explain and not a lepton number. The universe may have a non-zero lepton number too, but part of the leptonic content of the universe is all those neutrinos I talked about at the beginning, which were made in the Big Bang. Nobody knows how to detect those neutrinos, much less measure their lepton number. What we can measure is the baryon number in several different ways, Big Bang nucleosynthesis, for example. So this we know, and this is what we'd like to explain. And there is, in fact, a leptonic scenario known as Lepto Genesis, which can explain it, and I'd like to go through that with you. Lepto Genesis is a consequence of the most popular theory of why neutrinos, though they have non-zero masses, weigh so little. That theory is called the Seesaw Mechanism, and it associates with the familiar light neutrinos very heavy neutrino seesaw partners called N. And the way the arithmetic works, the heavier the N's are, the lighter the neutrinos are. Hence the name seesaw. It's this game where a child sits on each end of a board which goes up and down. Now when we say very heavy neutrinos, I'm talking 10 to the 10, 10 to the 15 GeV. You're not about to make these neutrinos at the LHC or any other accelerator. However, just after the Big Bang, it was hot. Very hot. Hot enough that the average energy per particle was enough to make these masses. So these neutrinos would have been there, if the seesaw is right, just after the Big Bang. Now, it is a signature feature of the seesaw that both these heavy neutrinos and the light ones, which we see today, are their own antiparticles. So that's another motivation for looking for neutrinoless double beta decay. If a heavy neutrino is its own antiparticle, that means it doesn't know whether it's a lepton or an antilepton. It can decay into either one. It can decay, for example, into an electron or into a positron. However, if neutrino oscillation violates CP, if the anti-neutrino oscillation probability is different than the neutrino oscillation probability, then quite likely those heavy N decays in the early universe violated CP also. Because in the seesaw, these two CP violations come from the same place. They come from a matrix of so-called Yukawa coupling constants, Y, which couple these heavy neutrinos to the Higgs doublet of the Standard Model and the Standard Model lepton doublets, each of which contains a neutrino and a charged lepton, and there are 3 of them, 1 for each family. Now, if these heavy neutrino decays in the early universe violated CP, then that means that for CP mirror image decays like this, the CP mirror image of N is N itself, because it's its own antiparticle. The CP mirror image of an electron is a positron, and the CP mirror image of H plus is H minus, where H plus and H minus are the charged Higgses in the Standard Model Higgs doublet. Now, that may be confusing. Somebody probably told you that there's no charged Higgs in the Standard Model. And what they mean by that is that the charged Higgs has been absorbed by the W plus to make the longitudinal spin state of the W plus. But that's today. That's not in the early universe. Before the universe cooled through about 100 GeV, where the Higgs vacuum expectation value turned on, this particle was just a member of the Higgs doublet, and the W boson didn't have any mass at all. So at the time I'm talking about, that's an ordinary particle, and it's available for this decay. And if CP is violated, then the rates for these two CP mirror image decays are different. Just like if CP violated is violated here, nu and nu bar oscillate differently. And if these two rates are different, then after these decays have occurred, there's more electrons than positrons, or the other way. The universe has unequal numbers of leptons and antileptons. Now, of course, what we're trying to explain is that the universe has unequal numbers of baryons and antibaryons. Step one gets us as far as the leptons. Then there is a step two. In step two, a standard model process predicted by the very well confirmed standard model of Glashouse, Lyman, Weinberg, a standard model process called the Sveileron process, which is non-perturbative, which does not conserve the baryon number, which distinguishes neutron from antineutron, or the lepton number, which distinguishes electron from positron, but does conserve their difference, acts. And the nature of the Sveileron process is such that if you start with the sort of universe which would have resulted from CP violation in N decays, which has a non-zero lepton number because it has unequal numbers of electrons and positrons, and similarly mu pluses and mu minuses and neutrinos and antineutrinos. If you have this zero lepton number, still no baryon number, and you input that into the Sveileron process, then out comes a universe which still has a non-zero lepton number, but now also a non-zero baryon number, approximately minus a third of the original lepton number, such that B final plus L final is minus L initial, which is equal to B initial minus L initial. So B minus L has been conserved, but now there is a non-zero baryon number. And that's what we were trying to explain. And it's observed that this works quantitatively for very reasonable values of the parameters. Not only do you get a non-zero baryon number, but you get the observed non-zero baryon number, the observed number of baryons per cc relative to the number of photons per cc in the universe. So this is a very, very tempting hypothesis. It depends on the seesaw. We don't know that the seesaw is right, but if the seesaw is right, then leptogenesis falls out of it. It's unavoidable at some level, provided that there are CP violating phases in this matrix. And if indeed the matter of which we are made came from those heavy neutrinos, then we all come long ago from those heavy neutrinos. We are their children. Yes?
But this still hinges upon the quite likeliness, so to say, of these heavy neutrinos also decaying like, behaving like the nearly massless neutrinos would. But what do you mean by the statement quite likely then?
I think maybe the best time to answer that question is after we've gone on just a little bit. But if I fail to answer it, harass me so I will answer it. Yeah?
Sorry? When you started discussing Majorana neutrinos, you sort of explained that lepton number is not a really well-defined quantity there.
Right?
But in the Lepto Genesis case, you still use it all the time. So how does this work?
Right. The lepton number that we're talking about can certainly be defined, but it is not conserved. And the fact that it is not conserved is essential. Let's go back. Before these decays occurred, we might have had electrons and positrons, but we would have had them very likely in equal numbers, for the same reason we would have had baryons and antibaryons in equal numbers. After these decays occur, if there is a CP violating difference between the rates, we have unequal numbers of leptons and antileptons. So manifestly, lepton number has not been conserved, and we are using that crucially. So I'm just using lepton number as a framework in which to talk, but it's not a conserved quantum number. That's crucial. And when you get here, oh, sorry. when you get here, the baryon number isn't conserved either. That's how we get from the non-zero lepton number to the non-zero baryon number.
My point is more in your previous slide, you define lepton number as different numbers of E minus and E pluses, and that I see.
Yeah,
But you also have loads of mu's and u bars that constantly switch into each other.
that's right. So in addition to these decays, there are decays in which heavy N goes to neutrino plus H0 or antineutrino plus H0 bar. That's right. Then we have these neutrinos and antineutrinos, and by this point, the temperature of the universe has come down to the degree, what a choice. The temperature has come down to the degree that at least some of those primordial neutrinos from the Big Bang are non-relativistic. They may all be non-relativistic, but at least some of them are. That is, the temperature is below the mass of the heaviest of them. Now, so long as a neutrino is relativistic, I told you that when a nu interacts, it makes an L minus and a nu bar makes an L plus. And if nu bar and nu are the same, apart from polarization, then the polarization is enough that the left-handed guy makes L minus and the right-handed guy makes L plus. But once the neutrinos become non-relativistic, those helicity quantum numbers are not defined anymore. And I just have a thing there, and if it should make a charged lepton, it can be of either persuasion. So I deliberately didn't want to go there, but when I answered an earlier question, but since you ask it, it's not only that we can't measure the lepton number of the universe because of the fact that there are neutrinos there, it is also, as you correctly call attention to, that the lepton number of the universe is not defined because we have all these neutrinos and other neutrinos, and some of them have their spins up and some of them have their spins down. And so long as they were relativistic, I could have used their polarizations as a kind of a proxy for lepton number. No lepton number, but the polarization also results in a differentiation of what they do. Once they're non-relativistic, they don't have these polarizations anymore. And you're quite right. But we can still talk about lepton number. We just have to understand a bunch of things about it. It's not conserved. We can't measure it. It's not well defined. But we can still talk about it. Am I clear? For these purposes, we can talk about it. Yes?
I understand for this whole argument to go through, you anyway need the Seesaw mechanism to work independently, right?
Yes.
Are there any ideas on how to test that one experimentally?
Oh, a tough bunch. Well, you have put your finger on what is the most challenging aspect of both the Seesaw mechanism and Lepto Genesis. I think they are both very appealing, but they are both very challenging to try to figure out a way to actually confirm experimentally. It is a signature of the Seesaw that Majorana masses are present. The Majorana mass is a key ingredient of the Seesaw. That means you want neutrinoless double beta decay to occur. If you have experiments very, very, very much more sensitive than the present ones, and they still don't see anything, I, for one, would become skeptical of the Seesaw. On the other hand, if you do see neutrinoless double beta decay, while that increases the plausibility of the Seesaw, it doesn't prove it, obviously. There could be other lepton-violating processes than Majorana masses, or there could be Majorana masses, but not the Seesaw.
Is there a minimum Majorana mass which you would have to detect so that the Seesaw mechanism?
Yes, but no, and what in the world do I mean by that? There is a minimum Majorana mass for a reasonable Seesaw. It's like the question, does chocolate come in colors other than brown? To which the answer is, do you have a reasonable question about chocolate? The reasonable minimum Majorana mass I would say is bigger than the Dirac masses of the quarks and the charged leptons. So the top quark is there, TeV. You can talk about Majorana masses smaller than that. You can have Majorana masses that are 10 to the minus 5 electron volts, but you don't have a seesaw mechanism with that kind of a Majorana mass. The seesaw depends on the Majorana mass being bigger than the other masses, much bigger. Moving right along. Now we come to the other part of the question, how do you get evidence for these things? We just spoke about the seesaw. Now let's talk about leptogenesis. Leptogenesis is based on the seesaw idea that there are these very heavy particles that would have existed in the early universe. Too heavy to be made in the laboratory today. So how can you test leptogenesis? There are variations that people are working on, I'm working on one myself, where the heavy neutrinos are actually within range of the LHC. So potentially you might actually be able to create them, and then you could study their decays and you would see that they have these CP violating decays. That would be extremely nice. However, in plain vanilla seesaw pictures, that's not the way it is. They are very heavy. So you have to do something else. And that something else depends on this link that I spoke about before between CP violation in heavy neutrino decays in the early universe and CP violation in neutrino oscillation. And here I hope to explain what I mean by likely. In a convenient basis in which the mass matrix for the heavy neutrinos has been diagonalized, and in which the mass matrix for the charged leptons has been diagonalized, the Yukawa coupling matrix that I called Y, which couples the heavy neutrinos to the Higgs and the light leptons, is the only source of CP violation among the leptons, no matter what experiment you do. N decays in the early universe, neutrino oscillation today, mu goes to E gamma, anything that's leptonic, the only place that CP violating phases can occur is this matrix. Nothing else is complex. Now, this set of couplings is responsible for N decaying into the Higgs and the light leptons. But it has another role. As the universe cools through roughly 100, 200 GeV, the neutral Higgs field picks up its famous vacuum expectation value in the Standard Model. Now particles have masses, other than those heavy neutrinos which had masses from outside the Standard Model right from the get-go. Once that happens, the neutral Higgs piece, I haven't written out the neutral and the charged pieces separately. The neutral Higgs field here develops a vacuum expectation value. It's about 175 GeV, and hence you get a term in here which is Y multiplied by that VEV, which I call V. That's just a constant, and when I have a fermion coupling like this times a constant, that is the same sort of mass term that the quarks have. It is called a Dirac mass term. So once the VEV kicks in, you get a Dirac mass for the neutrino, and it is just the VEV times this coupling matrix. In terms of this Dirac mass, the diagonal mass matrix for the heavy neutrinos, whose diagonal elements are just the masses of those heavy neutrinos N. Masses, so they're real numbers. And this mixing matrix, which we have been talking about and which we claim is unitary, here is the seesaw relation. This is the matrix which has been diagonalized and whose diagonal elements are the masses of the light neutrinos. So notice m nu is inversely proportional to mn. That's the seesaw. The bigger mn is, the smaller m nu is. But now let's look at the phases. This is a matrix of masses. It's a real matrix. If leptogenesis took place, it came from phases in Y. Hence, Y must be complex. And hence, MD, which is just Y times a number, must also be complex. But MN is real. If MD is complex, then unless something really unexpected happens, what's in this parenthesis has to be complex. But this is also a matrix of real masses. It has to be real. If this inside the parenthesis is complex and that is real, the mixing matrix had better be complex to absorb the phases inside here and make M nu real. But if the mixing matrix is complex, then because of that formula reproduced here, through this imaginary part, there's going to be a CP violating difference between neutrino and antineutrino oscillation probabilities. So to say it again, if leptogenesis occurred, Y and hence MD are necessarily complex. Hence, unless something unexpected happens, this parenthesis is complex too, which requires that you also be complex to make M nu real. Now, it is possible for what is in this parenthesis to be real even though MD is not real, and then U can be real and we don't get an imaginary part there. However, I submit to you that that is not the natural state of affairs. If this is to be real despite the fact that MD isn't, and despite the fact that the physics of MD is the physics of this interaction, and the physics of MN is some Majorana masses that have nothing to do with interaction, and so these two matrices have nothing to do with one another. If that's to be complex, and yet what's in this parameter, or what's in this parenthesis is to be real, I consider that quite unlikely. And that's what I meant when I said it's likely that that does not happen. Can it happen? Yes. If we're naughty and we want to do it on purpose, we know just how to do it mathematically. But I don't think that's very likely. Consequently, you expect, if leptogenesis occurred, that neutrino oscillation does violate CP. And consequently, people are gearing up to look for that CP violation. This is the question, and people want to answer it experimentally, and I am going to skip the next slide because I want to conclude. No, come on, you. Yeah, I'll skip that too. I've described what we would like to do in terms of the physics of neutrinos as we currently understand it. But there may be surprises. And to illustrate that there may be surprises, I'd like to tell you about some surprises we have already experienced within the last year. One of them bears on sterile neutrinos. The question is, are there more than 3 mass eigenstates? And what you'll see is related. Are there sterile neutrinos? What the LS&D experiment reported years ago is a rapid nu mu bar to nu e bar neutrino oscillation. And I'm using this II Neutrino approximation. They found that their neutrinos already oscillate when L over E is of order 1. in these units, which means that the delta m squared that they require is also of order 1 in those units, 1 eV squared. But 1 eV squared is much larger than the atmospheric and the solar delta m squareds, which together describe successfully all other oscillation experiments. If LS&D has really seen an oscillation so that there is a third delta m squared, then there must be at least 4 mass eigenstates. 1, 2, 3. This can be one of these, but then there's a fourth. So there are at least 4 mass eigenstates. Since they are orthogonal eigenstates of the Hamiltonian, I can form 4 orthogonal flavor eigenstates as linear combinations of them. Now, from measurements of the invisible width of the Z boson at LEP, we know that when this decays to neutrino pairs, it only decays to 3 different neutrino flavors made up out of light mass eigenstates. The invisible width has been measured, and it has been translated into the different numbers of neutrinos that the Z decays into, and the answer is something like 2.98 plus or minus 0.02, which sounds suspiciously like 3. So only 3 flavors couple to the Z. Hence, if there are more than 3 mass eigenstates, and hence more than 3 flavors, the additional flavors don't couple to the Z. That's an experimental observable.
What if the work of mass is twice the Z mass?
These particles are not likely to have twice the Z mass. What you say is true, but that wouldn't fit with LS&D. They're calling for masses around 1 volt. Oh, of course, the splitting could be 1 eV squared, and the mass is 3/4 of the Z mass, but come on. And in the standard model, flavor neutrinos that don't couple to the Z don't couple to the W either. That comes from the weak isospin structure, the I weak equals a half structure of the doublets, and the I equals 1 structure of the Z, and so forth. And such neutrinos that don't have standard model interactions, coupling neither to the Z nor the W, are what we call sterile neutrinos. So what LS&D hints at is the existence of sterile neutrinos. The question is the LS&D signal genuine neutrino oscillation? The mini-Boon experiment at Fermilab is trying to confirm or refute LS&D. Now in mini-Boon, both L and E are about 17 times larger than they were in LS&D, but L over E, their ratio, is still about the same as LS&D, namely 1. And mini-Boon last summer just released its first nu mu bar to nu E bar results. This is the same reaction that LS&D looked at. And here are the results. The mini-Boon results are in red. The corresponding LS&D results are in black, plotted versus L over E. And what's plotted here is the probability for nu mu bar to nu E bar as seen by mini-Boon or as seen by LS&D. Now what you see is LS&D saw some effect. Mini-Boon also sees some effect, non-zero oscillation probability. Moreover, although the error bars are big and they need to be shrunk through further data taking, and that's what mini-Boon is doing, qualitatively, the mini-Boon data look like they do the same thing as the LS&D data. Well, I think approximately nobody expected the mini-Boon data to look like that. Most everybody, including the members of mini-Boon, expected that when they take a look at the data, they'll see flat at 0, nothing. Surprise. So do LS&D and mini-Boon see a genuine oscillation, the same oscillation as each other? I don't know.
You can take the oscillation length change directly from this?
There are pretty big errors. So what you get is a region in delta m squared and sine squared 2 theta space. And the interesting thing is that the two experiments are consistent with a non-zero oscillation and consistent with each other in those terms. So it's not a unique point in that space, but it's a region.
How many standard deviations is this from zero? Well,
3 times 10 2.
3. A second surprise. This one has to do with the possibility that neutrinos interact with matter in a way that's outside the standard model. There's an experiment called MINOS, which sends a beam of neutrinos from Fermilab about 735 kilometers to a distant detector. They look at a number of things, but one of the things they look for is disappearance of muon neutrinos, or what is equivalent, the probability that they don't disappear. That's what's referred to here, the probability that a new mu is still a new mu when it reaches the detector. And within the last year, the anti-neutrino analog. Now, everybody expected that these two probabilities would be the same as each other, but experimentally, maybe they're not. In those two parameters that I was just referring to, in blue here is the allowed region for the neutrino data, the allowed region in delta m squared and in sine squared 2 theta. These are the parameters without, well, I hope the axis is clear. This is sine squared 2 theta. No, this is delta m squared. This is sine squared 2 theta. In blue, the allowed region for neutrinos. In red, the corresponding allowed region for antineutrinos. Now, the solid curve is the 90% confidence level curve. I think that's the one you should look at. At 90% confidence level, there is a sliver of overlap where the two results are consistent, but there's obviously some tension. Now, within the standard model, you cannot explain this. If you can neglect all of the interactions of neutrinos and antineutrinos with matter, then these two things have to be equal to one another unless CPT invariance is violated. And I, for one, am very reluctant to give up CPT. On the other hand, these neutrinos do interact with matter. They do that when they are being produced. They do that in the detector, obviously, as they make something in the detector. And they do that as they pass through Earth matter on the way from Fermilab to the detector. These people have shown that non-standard neutrino interactions can explain this disparity. And the non-standard interaction that they have used to explain it is one in which a new tau, when it reaches the detector, makes, contrary to what I said at the beginning, not a tau, but a muon. That does not happen in the standard model. When you go back and you rewrite this, in the pre-mixing form, L alpha couples only to nu alpha. A new mu makes only a muon. A new tau makes only a tau. They have a new tau making a muon, so it's outside the standard model. But if you allow this kind of interaction, then they can explain this pattern. I don't know where either of these surprises is going. I don't know if these effects are going to hold up, but there they are, and I describe them to you just to underline the point that as you do neutrino physics, you may think you can anticipate the general nature of what you're going to see, and you may be in for a very big surprise. In summary, good luck to all of you.